Hi, welcome to my presentation. I'm here to talk to you about an exciting and developing field called quantum computing. Computing begins with Alan Turing. He made an invention that would change the world. Some scientists call it the Turing machine, but most refer to it as a computer. Modern encryption is based off the RSA algorithm, in which two large prime numbers are used to hide a message. But if you could guess what the numbers were, you could possibly decrypt the message. However, Turing machines are not good at finding these numbers, and quantum computers might be better at it. In fact, there's many problems that quantum computers could likely do better than Turing machines. Another example is the simulation of how a protein is formed, and other quantum systems. One way to make a quantum computer is to use cold trapped ions. These are modeled as quantum harmonic oscillators. Quantum information can be stored in the frequency and angular momentum of the ions within the trap. Furthermore, additional ions can be added to the trap to store more quantum information. However, if too many ions are in the same trap, they become hard to control. We need to find control over the ions to do computations on them. For example, the ground state can represent a logical false and the excited state can be a true. If we accidentally flip the state of the wrong ion, though, the calculations will be wrong. The important calculations are rotations and C0 gates. These two calculations are universal, meaning we can make any other calculation just using different combinations of these two. A rotation is an added phase to the superposition between the two logical states of a quantum bit. So the ions in the trap can be in a superposition of the ground state and the excited state, and then we can use some lasers to do a rotation, and now we'll pick up some phase. The C0 gate is a 2-bit gate, so one bit is the control and the other is the target. And if the control bit has some component in the true, then that component will be used to add phase to the data bit. And that essentially functions as a controlled NOT gate. This gate is special because it preserves the superposition of the quantum information and it can entangle the particles. We can build these gates simply using lasers, and we can target the ions within the trap and excite them or pump them through several quantum state transitions just using lasers in the trap. Another important aspect of computers is being able to get the information out of the computer. Your computer wouldn't be very useful if the monitor was broken. In an ion trap quantum computer, this can be done with optical pumping. In optical pumping, we power transitions between different states using a laser, and in one state, the logical true, the laser will induce the ions to emit photons, and we can detect these photons, so we know it's in the true state. But if it's in the false state, no photons will be emitted, and so we can build a picture of the information inside. Quantum computers can also be scaled by adding more traps. If the ions in the trap get too concentrated, then it's going to be hard to control, but having more traps makes this problem somewhat go away with the scaling. However, this does add some additional complexity because the ions need to be moved quickly in between the traps, and you can induce more error while you move them. And it also requires that we recool the ions after moving them. An interesting technique for cooling the ions is called sympathetic cooling. Instead of moving single ions, we can pair two different species of ions together, and then we can target the lasers to cool one of the ions, and it won't disrupt the quantum information in the other ion in the pair. However, since the ions are motionally paired, the cooling will be exchanged between the two ions, and both the ions will be cooled. Trapped ion quantum computers have many useful properties, and they will need to continue to be explored, particularly the ability to control the ions within the trap and dealing with the errors. As mentioned, moving the ions between the trap can introduce additional errors, but some of this has already been mitigated through decoherence-free subspaces. Since the ions are already in pairs, we don't actually need to use the physical quantum states to represent the information. We can use combinations of physical states to represent the quantum information, and this can be more robust against errors. Still, many improvements will need to be made before quantum computers become much more useful than classical computers. Thanks for learning. Talk to you later.